Welcome to the deep dive. Today we're tackling something, well, massive. Literally. It's that huge headache in manufacturing trying to get pinpoint precision and decent efficiency when you're dealing with enormous industrial parts. I mean, picture these multi-ton components, right? Giant aerospace frames maybe, or huge dies for car bodies. They often need milling, then drilling, then super precise grinding, and traditionally that means stopping, unclamping this beast, somehow moving it to another giant machine, clamping it again.
And hoping everything lines up perfectly again.
Exactly. And each move isn't just slow and, frankly, dangerous. It's another chance for tiny errors to creep in. Misalignment, which leads to costly scrap. You can just grind everything to a halt.
It's a classic bottleneck, a huge one.
So if that's the problem, where's the solution? Today we're diving into a specific piece of tech, the CNC Gantry Grinding Machine. It sounds specialized, and it is. Our mission here is to unpack how these machines are kind of revolutionizing large part production. We want to understand how they hit that sweet spot of incredible precision and efficiency, cutting through those bottlenecks we mentioned.
Making the impossible feel a bit more possible.
Yeah. We'll look at the core advantages, the design features, the capabilities that make them so vital for really demanding industries. So, maybe to kick us off, what is it fundamentally about these machines? What makes them the answer for these huge workpieces where standard machines just, throw their hands up?
Well, what's really interesting is that it's not just one thing. It's a combination, a synergy of design ideas working together. The core concept behind a CNC gantry grinder, CNC meaning computer numerical control, so highly automated, very precise, is that it tackles those large part problems head on. It does this by combining incredible structural rigidity, really efficient automation, and this unique ability to handle complex surfaces on truly enormous parts.
Okay. Rigidity, automation, complex surfaces.
Right. And that combination, it directly cuts down on manual work, boosts the quality significantly. But, as you hinted at, the very first hurdle, it's just getting that massive workpiece onto the machine bed safely and efficiently.
Yeah, that sounds like step one and maybe the hardest step sometimes. How do you even start?
Exactly. For many traditional machines, that loading process is a major headache.
So how does the gantry design specifically make that easier? That whole slow, risky process of loading multi-ton parts, how does it simplify things? Okay, let's unpack this.
So the genius of the gantry frame is its structure. Think of it like a bridge. It creates this wide open access, both from the top and from the sides. And here's the key difference. The gantry, the bridge part with the grinding head, actually moves over the workpiece, which stays completely still.
So the part doesn't move, the machine moves over it.
Precisely. This means you can use an overhead crane, lower several tons straight down onto the work table. There's nothing in the way, no complex maneuvering needed.
Like dropping an engine block straight into a car.
Exactly, that kind of direct placement. What's fascinating here is how much complexity that removes. It drastically cuts down the setup time. We're talking hours saved sometimes, compared to conventional machines where you might be shuffling things around.
And I guess if the part stays put, you could machine multiple sides without moving it.
You got it. For components needing work on, say, 5 faces, this design often allows all of that in one single setup, one clamping. That eliminates all those risky intermediate transfers between machines. Huge efficiency gain right there.
That is clever.
Yeah.
Just rethinking the whole loading dynamic. Okay, so the part is loaded. Now, the next challenge you mentioned, grinding something incredibly long, maybe dozens of meters, perfectly flat. That just sounds physically impossible.
Yeah.
Wouldn't the part itself sag? Or the machine bed flex under that weight and length? Here's where it gets really interesting. How do they achieve that level of flatness?
This really comes down to that exceptional rigidity we talked about. The gantry frame itself is engineered to provide incredible structural integrity over the entire working length. This massive, stable structure essentially prevents any significant sag in the workpiece or vibration in the machine during the grinding process.
So it's just brute strength, basically, a super rigid frame.
It's engineered strength, yeah. These frames are typically made from really heavy, aged cast iron or sometimes specialized welded steel constructions. The key is they're stress relieved, meaning internal tensions in the material are removed so they don't deform over time or under load. Plus, they use extremely precise guide rails, the paths the gantry moves on, which also help dampen any tiny vibrations.
Okay, so it's stable, but how does that translate to perfect flatness end to end?
The true advantage here is that because the frame is so rigid and the workpiece is stationary, the grinding head can travel the entire length of that part, maybe 20, 30 meters, sometimes more in one continuous path.
Ah, one smooth operation.
Exactly. There's no need to stop, unclamp, shift part, reclamp, and start again. Every time you do that, you introduce a potential for a tiny misalignment, a small error.
Which adds up over a long part.
It absolutely does. This single setup, continuous pass guarantees consistent grinding pressure, minimizes any deflection, and allows them to achieve really impressive accuracy. We're talking repeat positioning accuracy, often down to 2.00005 millimeters.
Plus or minus 5 thousandths of a millimeter. That's thinner than a human hair.
Right. Over potentially huge distances, yes. It's quite remarkable. Think about grinding a guide rail for another large machine tool. It has to be perfectly straight and flat. This makes it possible.
That kind of precision is just staggering. It makes me think immediately about industries where even tiny errors are catastrophic, super expensive. Automotive molds and dies come to mind. They're massive, complex.
Absolutely. Automotive is a perfect example. If we connect this to the bigger picture there, especially for mold and die making, these gantry grinders are, well, they're game changers.
What specific advantages do they bring to that world?
It's really two main things for molds. First, they deliver that extreme precision needed for the complex, curved surfaces of a mold. But maybe even more importantly, they often act as complete machining centers. They can perform multiple operations in just one setup.
Oh, so not just grinding.
Right. Many of these machines are equipped to do face milling, drilling, tapping, and the final precision grinding, all while the mold base is clamped just once.
So you skip moving it between a milling machine, a drilling machine, a grinder.
Exactly. Think of a huge mold base for, say, a car door panel. Instead of moving that chunk of metal maybe 3 or 4 times, risking misalignment each time, it stays put. This multi-process capability saves a massive amount of handling time. Seriously, for large mold plates, you could save over an hour per plate just by eliminating those extra setups.
An hour per plate. Wow.
And when a mold has multiple plates, that adds up very quickly. Combine that with high-speed cutting capabilities, and we've seen cases where the overall machining cycle time for a typical automotive body panel mold can be shortened by over 50%.
50%. That's huge for meeting production deadlines.
It's critical. It helps car manufacturers hit those incredibly tight delivery schedules. And because the process is so stable and precise, you get consistent quality. That means a much higher yield rate, much less costly scrap, which, for expensive molds, is a massive financial benefit.
Right, so for molds, is that multi-process power, reduced setup, faster cycles, better quality. Makes total sense. Let's broaden out a bit then, beyond molds. Just thinking about overall efficiency, large part grinding generally. It's known for being slow, right? Creating bottlenecks, tying up really expensive machinery. How do gantry grinders tackle that general efficiency problem?
Yeah, large part grinding can definitely be a bottleneck. The efficiency gains come from a few areas working together: smart process optimization, advanced machine automation, and using the right high-performance abrasives.
Okay, break that down. What do you mean by process optimization?
Well, it often involves separating the grinding into distinct passes. You might have a roughing pass first, designed purely to remove material quickly, maybe using a coarser grinding wheel. Then you follow up with one or more finishing passes for the high precision and surface quality. Optimizing the parameters for each stage makes the whole thing faster.
Got it. Rubber first, then fine-tune. And the automation part.
Automation is key here. A really important feature is an automatic tool changer, or ATC. Think of it like a robotic arm that can automatically swap out the grinding wheels. So the machine can switch from that roughing wheel to a finishing wheel, or maybe to a different shape of wheel for a specific feature, all without needing an operator to step in and do it manually.
So the machine just keeps running.
Pretty much. It minimizes downtime dramatically. This allows for a nearly continuous operation, 24/7 if needed, which is vital when you're machining parts that might take many, many hours to complete. Maximize that machine uptime.
And the abrasives. Does the grinding wheel itself make a big difference?
Oh, absolutely. It's critical. Using high quality, what we call super hard abrasives, makes a huge difference in removal rates and wheel life. We're talking materials like diamond wheels, or more commonly for steels, CBN wheels, that's cubic boron nitride. It's almost as hard as diamond and very effective on ferrous metals.
So harder wheels cut faster.
Essentially, yes. When you pair those advanced abrasives with a powerful spindle that's the motor turning the wheel, you can remove material much more quickly and efficiently, especially during those roughing passes. Of course, selecting the right type of wheel, the right grit size for the material, and the finish required, that's all part of the process setup. And maintaining a strict schedule for dressing or replacing worn grinding heads is also vital for keeping efficiency up and quality high. A dull wheel is slow and produces a poor finish.
So it's optimizing the steps, automating the tool changes, and using the best possible grinding materials.
Exactly. It's that combination that really unlocks the efficiency potential for these very large components.
Okay, so bringing this all together, the core message from our deep dive seems pretty clear. For gantry grinders, the main story is twofold. First, achieving that extreme, almost unbelievable precision on truly massive parts.
Right, the kind of precision that was incredibly difficult or impossible before.
And second, doing it with unparalleled production efficiency compared to older methods. That unique, rigid, open frame design is key. It solves the loading nightmare, ensures that amazing flatness over huge lengths.
Making it invaluable for those really tough industries, yeah. Aerospace, automotive molds, energy components, machine tools themselves.
Absolutely. So that leads us to the final thought for you, our listeners, to maybe chew on. What does all this capability actually mean for the future of manufacturing, particularly for these massive critical components? How might the wider adoption of these super precise, highly automated, large-scale tools start to reshape industries, maybe even ones we haven't discussed? Or could it even enable totally new technologies that rely on components built to this scale and accuracy? Something to think about.